On Monday, I think I said amazing new idea every week, and the amazing new idea for this week is the one about procedure as data. And since you just got introduced to that idea, it's possible that you don't get right away what an amazing idea it is. So let me tell you that you could build a programming language consisting of Lambda, the thing for generating procedures, and the ability to call procedures, and nothing else. And that language will be universal in the sense that anything that any computer language can do, that language can do. You don't have to have, for example, arithmetic built in. You can make that out of just Lambda and procedure calls. You don't have to have any special forms except Lambda. In particular, I think this week's Extra for Experts is about figuring out how to do without define and still be able to write recursive procedures. How do you make a recursive procedure without being able to give it a name with define? Just with Lambda. That's the Extra for Experts this week. So it really is a very, very powerful idea. And what we used it for, as in this keep example, is generalizing patterns of control. So lots and lots of times you have a problem in which you want to do some kind of filtering of data. I have a collection of data, and I want to keep all the ones for which such and such is true and discard all the ones for which such and such is false. And that pattern is captured by this keep procedure. All of the control mechanisms that you typically get in programming languages, like for loops and while loops, all of those things, you can build using procedures as data, because a procedure is a representation in the computer of an action. So if you think about the language you learned in high school, you're saying, for I equals 1 to 10, do this. The do this is a procedure, or can be represented as a procedure. So we can have a for procedure that takes a start value and an end value, and lambda of I, do such and such, and creates that control mechanism. So any mechanism that you want for specifying the flow of control, sort of the sequence of events, what's going on inside the computer, can be made out of procedures as data. In this keep example, one way to look at it is as a specification of a sequence of events, but a better way to look at it is to forget about the sequence of events in the computer and just think about the problem you're solving as being solved all at once. So I have a collection of data. I want to restrict it to things that satisfy this condition. Boom, keep does that for me. So you don't have to think about, does this element satisfy the condition? OK, does this element satisfy the condition? You can imagine that happening all in parallel. And in some systems, in the not very far distant future, it might all happen in parallel. You might have a list of 1,000 things, and you might have 1,000 processors in that box on your desk. And each processor might be looking at a different element of your data, deciding whether to keep it or discard it from the result. So that's the power of having procedures as data. I wanted to generalize this notion about what should be data in the language by talking about the idea that's up on the chalkboard there about first-class data types. The data type is first class in a language if things of that type can be the value of a variable. So can I say define such and such to be that kind of thing? Can I do that for procedures? Yeah, I can say define square to be lambda of x times xx. Okay? So in this expression, I am defining the variable square to have as its value a procedure. In fact, this happens so often that, as you know, there's an abbreviation for it, where you'd say define parenthesis square of x. And what that abbreviates is assigning a procedure to a variable. A procedure can be the argument to a procedure. For any first-class data type can be an argument to a procedure. So as we've seen in the keep example, we can use a predicate function as an argument to keep. A procedure can be the value returned by a procedure. I haven't shown you that yet, but I'm about to. First-class data type can be a member of an aggregate. An aggregate is something like an array, where you take a bunch of different elements and you make one thing out of them. So far, the only aggregate data type that we have is sentences, and a procedure can't be a word in a sentence. But next chapter, we're going to see the more general mechanism of lists, and you can have procedures be elements of lists. So procedures are first class in that way too. And something that isn't in my lecture notes but is sometimes included in the definition is kind of the opposite of can be the value of a variable, namely can be anonymous. So you can have a procedure that doesn't have a name. So I can say, you know, lambda x word xx of, quote, foo, and get foo-foo, right? So I made this procedure that combines a word with itself. I didn't give it a name, and I could just call it, okay? In every language, numbers are first class. Yeah? Can you use lambda to define a procedure with more than two arguments? Yeah. The reason that this x right here is in parentheses, this one, is that it could be x, y, z, or x, y, z, w, or whatever names you want, and however many you want. Okay? Sorry, the question was, can you use lambda to make a procedure with more than two arguments? So yeah, you can. So numbers are always first class. Character strings are first class in some languages, but not all, notably not in C. Data aggregates are rarely first class. Instead, some languages give you a data type that's called a pointer to an aggregate. And those are first class, but it's subtly different from having the actual aggregate being first class. And hardly any language gives you procedures as first class data, although I'm pleased to say that that's changing. Python, up-and-coming language of the future, has lambda. Java, sort of the standard right now application programming language in the world, it doesn't have lambda, but it has something called anonymous classes, which you can use kind of as if it were lambda by standing on your head. So it's inelegant, but it's there. So the same people who kind of poo-poo the Lisp family of languages as being ivory tower-ish are starting to adopt the key central idea of Lisp, namely lambda, in languages out in the world because it's so very useful. People are starting to catch on to that. Okay, so in Scheme, one of the design principles, and one of the things I'd like you to get out of this course by the time we're finished, is a better idea of why is there more than one programming language? What makes people come up with different languages in different situations? And different languages have different design principles. One of the design principles of Scheme is everything first class. If it's in the language at all, it should be manipulable in all those ways. And Scheme does pretty well at that. We'll actually meet one exception down the road. But again, that's not the design principle that many other languages use. Many other languages use the principle of everything should be very efficiently compilable. That's not a terrible idea for a language, you know. I can understand that. Some languages use the principle that everything should look natural. I would argue with that one a little bit because people's idea of natural is so determined by programming languages of the past that it's a way of saying let's not have any progress in programming languages. But different design principles for different purposes. We're going to play later in the semester with Logo, which is a programming language designed for children. And we're going to look at how that fact led to Logo looking very different from Scheme, even though they're both sort of cousins in the Lisp family. Okay, moving on, I promised to show you how a procedure can be returned by a procedure. So here's the classic first example of that. I'm going to say define make adder of nums. Notice there's an implicit lambda in here. So I'm saying define make adder to be a procedure that has num as a formal parameter. And now the body of this procedure is going to be a lambda expression. Okay? So make adder says, take a number as argument, the domain of make adder is numbers, and return a procedure. The range of make adder is procedures. The returned procedure takes another number as an argument and adds num to it. So now I can say define +3. Notice no parentheses around +3. So there's no implicit lambda here. I'm going to say make adder 3. Now, what's +3 do? Well, if I say +3 of 8, I get 11. And define +5, make adder 5, +5 of 7. +5 of +3 of 2. Okay? So +5 and +3, let me make the screen bigger so you can see all that. So +5 and +3 are procedures by virtue of the fact that when I called make adder in the process of defining them, make adder returned a procedure. And it returned one procedure for the call make adder 3 and a different procedure for the call make adder 5. Okay? So I don't have to give it a name. I can say, this would be kind of silly. I don't know why you would do this, except just to show you that I can. Make adder 9 of 7. So I didn't have to say, OK, call this +9. I could just take the procedure that adds 9 to its argument, apply that to 7, I get 16. OK? So this is the first simple example of a procedure that returns a procedure. Now I'm going to show you one of my very favorite procedures in the whole world. It's this one. Define compose f and g. So you remember what composition of functions is from algebra class, right? The composition of f and g is the function that maps x to f of g of x. So I'm going to say that in scheme language, the function that maps x into f of g of x. Okay, there's compose. So compose first with but first of she loves you. Okay. So compose works entirely in the space of functions. Its two arguments are functions. Its return value is a function. So I can say, since compose first but first gives me the second word of a sentence, I can say define second to be compose first but first. Okay? So define twice of f to be compose ff. So I can say, did I define square? I think so. Twice square of 3. What am I going to get? 81. I'm getting the square of 3. So twice square is something that takes its argument to the 4th power. So this is really, really cool. This gives a very concise notation for building up more complicated functions as compositions of other functions without ever having to talk about the actual domain and range of the functions being composed. Right, so there's no x. When I say compose first but first, it really doesn't tell you what the domain of first and but first is. Now, in order for it to work, of course, it has to be that the domain of f includes the range of g. Otherwise, it doesn't make sense to compose them, right? But you can try, and you'll get some kind of error message when you actually run it. So it's not that you can completely not think about domain and range, but you don't have to have those little variables like x floating around. You can just say second is the composition of first and but first. Duh. Really nice. Anybody ever programmed in Pascal? A couple of people. Yeah, too bad. Pascal's a pretty useless language, but it's interesting to talk about for our purposes here, because in Pascal, you can use a function as an argument to a function, but you can't have a function as the return value from a function. That seems like a pretty arbitrary restriction, and it is. And the reason for it is, we're going to see a little bit in this course, and you'll see in detail in 61C, why it's relatively easy to allow functions as arguments and relatively hard for a compiler to allow functions as return values. So it was just sort of an efficiency decision that they made. All right. Let's come back to this. Yeah. Yeah, I mean, are compiled scheme programs big? Is that what you're asking? Oh, I see. Yeah. The source code in a scheme program will be smaller than in another language. Yes, and there are a lot of reasons for it. This thing that we're talking about is just one of them. Probably the most important difference is that we don't declare types of variables. And later on, we'll be talking about that in a week or so. 2 weeks, I guess. Talking about some of the ways in which this language differs from other ones that make program's easier to write. It matters because to a first approximation, he wanted to know about sort of differences in size between scheme programs or scheme data and other languages. And I'm making the claim that you can write shorter programs in Scheme that do the same thing. And it matters because, to a first approximation, the number of debugged lines of code produced by a programmer in a day is language independent. You can be using a very terse language or a very spread out language, and you'll still get, and it's a shockingly small number, like 2 or 3. And that's because of the word debugged. Right. You can write 100 lines of code in a day that don't work, but once you get it working, it averages out to a pretty small number. So therefore, the more you can fit in a line of code, the better in terms of getting the job done quickly. And that's why one of the ways that Lisp family languages have been used industrially is as rapid prototyping languages. So you want to write a program, you have a customer that you're writing it for. The customer gave you a spec, but of course customers never know what they really want. So you implement what the customer asked for, and the customer says, no, I don't want that, I want this other thing. And you go through 4 or 5 iterations of that before the customer finally gets around to everything's perfect except it runs too slowly. So those first 5 iterations are best done in a language that lets you write throwaway code quickly. So sometimes people will write the first 5 versions in Lisp, and then when they get to, it runs too slow, write it in C or something and try to optimize it from a time standpoint. Okay, let's move on. What's up on the screen here is a procedure for, I'm sorry, the world's most boring problem. I picked it because it's a question that has 2 answers, namely the roots of a quadratic equation. So if I want the roots of x squared minus 5x plus 6 equals 0, I'll say roots of 1x squared minus 5x plus 6. And what I get back is a sentence with the values 3 and 2, because those are the roots of that equation. I picked one that would come out nicely. So since a function can only return one value, I can't return the 3 and then separately later somehow return the 2. What I have to do is make a sentence right here that combines the 2 values. So what are the 2 values? You remember that from high school. It's minus b plus the square root of b squared minus 4ac over 2a, and minus b minus the square root of b squared minus 4ac over 2a. So the only difference is this plus sign versus this minus sign. All right? So that's a lot of redundant typing, and it's also a lot of redundant computation because it takes a non-zero amount of time to compute a square root. So it would be nice if we could just compute the square root once. So what we want to do is compute square root of b squared minus 4ac and give that a name. Oops. I can do that this way. So I'm doing roots ABC, and I have this helper function, an internal definition, roots 1, that has a formal parameter d. It's not just because it's the 4th letter of the alphabet. The d stands for discriminant, which, if you remember back as far as high school, is what they call this square root of b squared minus 4ac thing. And then I call roots 1 with square root of b squared minus 4ac as the actual argument expression. And then inside roots 1, I say minus b plus d over 2a and minus b minus d over 2a. and combine those into a sentence. Okay. Questions about how that works? Yeah. Yeah, he's saying it calculates it once rather than twice, only because scheme uses applicative order. That's right. If it were normal order, we would end up calculating that twice. Although we'll see later in the semester there's a fix for that. But yeah, but luckily scheme does use applicative order, so it does the right thing. Okay, so this solves the computing it twice problem, but it does so at the cost of having to define this helper, roots1, which I'm never going to use for anything else, and also separating the name D up here from its value down here. Right, so it's a little hard to read. So I'm going to solve those problems one at a time. I'm going to solve the first problem by making it even a little harder to read, actually. But instead of saying define roots1, I'm just going to have an anonymous lambda expression. This is the same thing that was the body of roots1. Here, let me see if I can get them both on the screen at the same time. No, I can't. Yes, I can. So here was the definition of roots1, and now down here is the lambda expression starting with this second open parenthesis. That's the same function as roots1, and then I call it, that's this open parenthesis in black, in white on black here, with square root of b squared minus 4ac as its actual argument expression. Okay, so there's no more name roots1, it's an anonymous function. But even though it's elegant in a certain sense, it's really ugly to read. So we have an abbreviation. What we're going to do is exactly this in the meaning of what we're doing. But we're going to rearrange this to put this D, this D right here, and this square root of b squared minus 4ac next to each other. The abbreviation is called let. So this is what a let looks like. And it is let here we go. Bindings body. So body is just like the body of a procedure. It's an expression that we're going to evaluate that will give us the value of the whole let expression. What's bindings? Well, bindings is open paren and then a binding, and then optionally another binding, and then another binding. As many as you want, and then close paren. Well, what's a binding? A binding is open paren, name, and then value expression. Okay? So when we put all that together, we're going to see this is the other case besides Conn where we have funny parentheses that don't mean call a procedure. This one does mean call a procedure. Namely, this is a call to the square root procedure from here to here. Okay, those are plain old function call parentheses. This one right here, having trouble just picking up one character, but this open paren is the start of a binding. And that binding extends all the way to here. Okay, so that's one binding. And then outside that are is the pair of parentheses that encloses the whole set of bindings. In this case, it's a set of length 1. Yeah? Isn't it a function? It's not a procedure call. We're not calling a procedure named D here, for example. Okay? That parenthesis has a different meaning. I mean, yeah, we're taking an action because of it, but we're not calling a procedure. Yeah? Good question. Can the bindings be dependent on each other? So let's look at a case, actually, with multiple bindings. So while I'm making this let, besides having D, I'm going to have a variable called minus B, whose value is the negative of B, and a variable called 2a, whose value is a times 2. And then the body can just use all of those variables to make a very, very short expression. So he wants to know, if I've defined D to be the square root of B squared minus 4ac, can I use D in defining the next variable? What do you think? Who thinks yes? Who thinks no? Ah, okay, you guys have seen let before, or you're smart, one or the other. The answer is no, and here's why. I might have the slide on. That's bad. I'm saying let D be this, and minus B be that, and 2a be that, and then the body. Now I'm going to unabbreviate that. I'm going to show you what it looks like using a lambda. In fact, I'm going to do it in 2 colors. So I'm going to start by saying lambda of D minus B and 2a. By the way, these are not really valid scheme symbol names, but STK is a little forgiving about symbol names. So lambda of that, and then the body of the lambda is sentence with plus and with minus. Okay? So that's the anonymous function that is hidden inside the let. And what I do with that function is I call it with the arguments square root of such and such, and then the negative of b, and then times 2a. Okay? So whoever asked the question, do you see that what I have is a procedure call as the outer expression that's calling a procedure that I just sort of custom built, right? So when I compute this expression here, the one where I have minus b, if there were a d here instead of b, does d have a value when I'm computing this expression? Who says yes? Who says no? Okay, somebody who says no, why not? 2 words. Applicative order. In Scheme, as in, by the way, most programming languages, all of these expressions get evaluated, all 4. The lambda expression, the square root expression, the minus expression, and the times expression. All of them get evaluated before we call this procedure. But it's only inside this yellow procedure that these variables have any meaning. Okay? Out here, there is no d. There's no minus b, there's no 2a. Those variables exist only in here. Okay? So we can't use this value in computing this value because they're computed independently. Now, it is a useful thing to want to do. Right? Use this value in computing that value. And so it turns out we don't really make a lot of use of it in this class, but if you're interested, there's a thing called let star. It's a terrible name. So, you know, A, 3, B, plus A, 5. Okay, that's good enough. So this is like a let. It's the same format of bindings, binding, name value. But here I'm using this name in computing this value. And the reason I get to do that in let star is that let star is actually translated to let one binding, A3, and then the body of that let is let B, whatever I said, plus A5, and then times AB. So it nests however many lets are necessary. So since this second let is part of the body of the first let, the variable A does exist here, and so we can use it in giving a value to B. So that's let star. Yeah. Yeah, he's asking, what if I wanted to do a let star using lambda instead of let? And yeah, I would turn this, using the same idea I did here, I would turn this into a procedure call of an anonymous procedure. And the body of that anonymous procedure would be a procedure call of an anonymous procedure. So there'd be a lambda inside an invocation inside a lambda inside an invocation. Yeah. You had a question? Can you make a recursive procedure inside a let? That's a very good question. I'm proud of you for recognizing that it's a problem. The reason it's a problem for people who aren't up to speed on this is in order to make a recursive procedure, it needs access to its own name. So if I say let foo be lambda of such and such, in that lambda, because that lambda is out here, the one that's providing the value for foo, there's no binding for foo. So I can't call foo inside itself. And so no, you can't use let to make recursive functions. There's yet another variant of let that's called letrec, L-E-T-R-E-C, stands for let recursive. And what it's an abbreviation for is so complicated that in the first 4 versions of the scheme reference manual, they got it wrong. You know, the Wizards of Scheme didn't quite get it right. But it is right now. You can look it up if you want to. Okay? So, where are we? All right. So what are the things that you have to understand about let other than just what the notation is? One is this is not like assignment statements in that programming language you learned in high school, because we're not making permanent bindings. It's not like saying, you know, x equals 5. Boom. The variables, the let variables, the d and the minus b and the 2a, are only usable inside the body of the let. If we go on to do something else after the let, they're not there anymore. Okay? Because they're arguments to this procedure. The actual values got substituted into this body right here, but they didn't get substituted into anything else. Okay? So don't think of it as being like assignment statements you grew up with. It just has a limited range. Secondly is the thing that you can't use one value to define the next unless you use let star or nested lets. There will come a time when you actually see that as useful, when you'll be glad that the let bindings aren't in effect while you're computing the values. Because you'll have some recursion or something, and you'll want to use old values of all three variables in computing the new value of all three variables. So sometimes let really is what you want, sometimes let star is what you want, and sometimes even let rec is what you want. Okay, questions? Wow, everybody understands. Okay, because I'm not asking questions because I get everything. I'm not asking questions because I'm so lost I don't know what to ask, or somewhere in between. Aha, a lot of thumbs down. Okay. Where'd you get lost? At let or at first class data? Yeah. Okay, remember the substitution model evaluation. He's asking about sort of the binding mechanism in the let. Remember the substitution model, and remember what it is that let abbreviates. So we compute, these things are actual argument expressions. They're all found next to each other, kind of, up here, along with the values that, along with the formal parameters that they go with. So it's a matching up of formal parameter with actual argument expression. So what does scheme do? First thing it does is it computes the value of all the sub-expressions. So we have an actual argument expression that's square root of b squared minus 4ac, and we compute that expression and we get 27, or whatever we get, okay? And we do that for all of the argument expressions. Then we substitute those values for the formal parameters in the body. So wherever there's a d in here, we're going to put 27. And wherever there's a minus b, we're going to put whatever the negative of b is, and so on. Okay? So now what we have is this expression, only it doesn't have any variables in it anymore, except for the global variables that are names of primitives, like sentence and slash and plus and minus. Then we just evaluate that expression, which is full of arithmetic functions and numbers and nothing else. Why do I need let star distinct from let? Is that what you're asking? I substitute them into the body, yeah. Oh, if I say let A3, I'm not sure I'm answering your question. Let me know. If I say let A3, we're going to substitute. Well, first of all, we compute this expression. It happens to be a very simple expression. Its value is 3. Okay? Now, every place there's an A, namely here and here, I substitute 3. So now what I'm left with is this inner let, which is the body of the outer let. So I'm going to evaluate that. This now says let B be plus 3, 5. It doesn't say A anymore. So plus 3, 5, that's 8. So I'm going to substitute 8 for B in the body of the inner let. So I get times 3, 8. Okay? Maybe if that yeah sounded like I haven't answered your question yet. Okay, sure. Other questions? Yes? The difference between using, okay, so let, so the way I did, if I had just said define D to be square root of B squared minus 4AC, yeah, I could have done that too as internal definitions, and that would work. No. Internal definitions are complicated to understand. When we get to chapter 4, you will learn that internal definitions aren't really definitions at all. They are an abbreviation for a LETREC. So it really all comes down to the same mechanism. Global definitions, things that you type at the scheme prompt, those are permanent. They leave stuff around. Global variables are generally frowned upon in the programming world because that's how you get in this situation where a change in one part of the program ends up affecting another part of the program that you weren't thinking about. So you want to keep all your variables local, and this is a way to do that. So the formal parameter of a procedure exists only inside the body of that procedure, and whatever notation you use ends up coming down to the same thing. Okay, but yeah, you could do it with internal defines. Okay, yes? Does let need a body? Yes, there is a body. In this bottom let, this part is the bindings part. Yes, the body of the let inside the let is times AB. Okay? And yes, let has to have a body. Yeah. In let start is the order of the bindings matter. Yes, because you can use A in coming up with the value of B, but not B in coming up with the value of A. And that's clear if you think about what it expands into, right? One of these lets is inside the other. Yeah. Sorry? If you use let instead of let star, then this expression, plus A5, won't use this binding for A. Instead, either it'll use some global value of A, or it'll give you an unbound variable error message. Okay? You guys, don't obsess too much over let. You can, go read all the stuff in the book and get to understand it. And you should understand it, but let is just one particular case of the general idea here. And I'd like to bring let back into that general idea, which is the ability to use procedures as data lets us build any control mechanism we want. Okay, so keep was an example of that. Every, which you're writing for homework, is an example of that. I talked about how you could write for as an example of that. And let itself is also an example of the same thing. That having procedures as a data type in the language lets us make any old kind of thing we want. You guys, I'm sorry, I hate to be, what's the word I want? Tendentious. But you're being really rude, and it does kind of make me feel jittery. So please wait until the class is over before you pick up your stuff. We are almost over, but we're not quite yet. If there's another question, I will answer it. Yes? Yeah, explain again why I can't use recursion with a let. So it's really the same thing as why in a regular let we couldn't use this A to define B. Do you understand that part? Because these expressions out here are evaluated before we have bindings for them. Okay, suppose one of these is a lambda expression. Okay, so I'd like to define a factorial function. I'm going to say let fact be lambda of n, and then, you know, if blah, 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 and in here someplace it'll be fact of n minus 1, right? Okay? And then I'll say, you know, fact of 5. Well, this is not in the body of the let. The body of the let is just fact of 5. So this whole lambda expression does provide a value for this fact here, but not for this one, because this gets evaluated before I've made this binding. So it's really the same as the A and B problem, except it's A and A. Okay? It's a good question. All right, see you next time. Oh, next time, sorry. The next 2 lectures are a videotaped presentation by Alan Kay about user interface design. Don't decide not to bother coming because it's a videotape. They're the best 2 lectures in the course. All right.